Okay, we can start. This is Mathematics for Economics, and I am Paolo Canofari. We can start considering an expression like y equal to f of x, and we can call this expression 1. This expression is known or is called function or transformation or mapping. And in this expression, we have two variables, variable x and variable y. The expression represents a relation which we suppose to exist between x and y. So, if we are in macroeconomics, x may be the total income and y the level of consumption. Expression y1 in this case represents the relation we suppose to exist between consumption and income. In the same way, we can consider x equal to the money stock in the economy and y as the rate of inflation. Expression 1 in this case represents the relation we suppose to exist between money stock and the rate of inflation. X is called independent variable and y is called dependent variable. A more complex expression is the following: y equal to f of x1, x2 until xn, and we call this expression 2. In this case, expression 2 represents the relation we suppose to exist between a dependent variable y and a set of independent variable x1, x2, xn. So in this case, we can consider x1 is, for instance, net income, x2, for instance, is the interest rate, x3, for instance, the total financial wealth, y is the level of consumption. So, expression 2 represents the relation we suppose to exist between consumption and on the other end, net income, interest rate, and financial wealth. Now we can define an economic model in the most general possible way as a set of implicit function. In this way, we can call this an economic or mathematical system. The first equation in the system is f1, so a big function, implicit function, of y1, y2 until yn, and x1, x2 until xn. This is equal to 0. This is the first equation of our implicit model. Then we have a second equation, f2, of y1, y2 until yn, and again x1, x2 till xn equal to 0. Finally, we have f1, f2, f3 until fn. So we have n equations in our system. Fn of y1, y2 till yn, x1, x2 until xn equal to 0. And we call this set of equations 3. This is a typical implicit form model in which we have a set of implicit functions equal to 0. Inside each type of function, we have a set of variables. Variable y1, y2 until yn are the so-called endogenous variable. So the endogenous variables are variables determined in the model, within the model. Variables x1, x2 until xm are the so-called exogenous variables. They are determined outside the model or are decided from someone else. So the difference is very important in economics because variables y1, y2 until yn are the variables determined in the model and are called endogenous variables. Exogenous variables are x1, x2, xn and are the variables determined outside the model or given in the model. How can we solve the model expressed in system tree? We can solve the model if we can write this system in the following way. y1 equals small f 1 of x1 until xm. In this case, the first endogenous variable y1 can be expressed as function, or can, depending on the set of the exogenous variables in the model, from x1 to xm. The same for the second endogenous variable, which can be expressed as a function of x1 until xm. So also the second endogenous variable can be expressed in terms of exogenous variables. Until the final yn, we can be expressed in terms fn, in terms of exogenous variables x1 until xm. And we call this system 4. System 4 represents the so-called reduced form model, in which each endogenous variable is expressed in terms of exogenous variables. So if we think to macroeconomics, for instance, y1 is consumption, or income is income, and y2 is interest rate, the two endogenous variables in our model. x1 and x2 are the two exogenous variables in our model, for instance, money stock and the autonomous components of the aggregate demand. If we can solve the model, we can write a reduced form the model. So the same as system 4 shows. If we can solve a model, we can also compute the so-called partial derivative of each variable, each endogenous variable, respect to each exogenous variable. We can write the partial derivative as delta yi respect to delta xj. This formula, this notation, denotes how a change in the exogenous variable xj can affect the endogenous variable yi. So for instance, how can we a change in the money stock can affect the interest rate or the equilibrium income. System in form 4, so the so-called reduced form model, gives also the equilibrium value for each endogenous variable given the exogenous variable. So if we consider change in one exogenous variable, for instance money stock or public expenditure or autonomous tax. In this case, we can consider the new equilibrium value for each endogenous variables by computing these partial derivatives. So considering the effect of the change in the money stock on the income or on the interest rate, for instance. In order to understand, we can now consider a model of two endogenous variables, for instance, the income y and the interest rate I, like is shown in the ISLM model, the standard ISLM model. We can consider a model in this way. If we solve the model, we have the net income y equal to delta 0 a plus delta 1, which multiply the real money stock ms divided by p, which means the real money stock. In the same way, we can consider the interest rate equal to gamma 0 a minus gamma 1, which multiply ms divided by p, the real money stock. We know that if the real money stock increases, we have a decrease in this interest rate. So if we compute, for instance, the partial derivative of y income respect to the money stock, the real money stock, we get, and we will see how to compute this partial derivative, the coefficient delta 1, which is the change in the in income when there is a change in the real money stock. At the same way, if we want to consider, we can consider the effect on the interest rate. In this model, the endogenous variables are interest rate and income. The exogenous variables are A, so the so-called autonomous components of aggregate demand, and the money stock MS divided by P, the real money stock. So we can consider also the effect of an increase in the money stock on the interest rate. And this can be obtained computing the derivative, the partial derivative on the endogenous variable I with respect to the exogenous real money stock delta ms divided by p, and this is equal to minus gamma 1. The negative sign is an assumption. It's an assumption because we assume that if there is an increase in the real money stock, the equilibrium interest rate decreases. This is a reduced form model. Why? Because exogenous variables are on the right and the endogenous variables are all on the left. So each endogenous variable, in this case y and I, is function or depend on the exogenous variable. In this model depends on A and on the real money stock and MS divided by P. Thank you.